Here's the 8008 Replica Mark 8 that I built over the last month, and it's running well. Not much trouble getting it going. A few bad ICs, but we have that taken care of now. And the current project, we're replacing the switch board up here, which is used for entry, monitoring, and all sorts of communication with the computer. And we're replacing that with a Arduino Mega. You can see that we temporarily got that wired in, along with an SD card for file storage. And we're sitting on the same platform as the original 8008. You can see that the original was larger than this Replica. A lot more space on the board between the ICs and this one, but that's fine. A fellow in the Netherlands went through and painstakingly copied these boards from the originals, so that was a lot of work. I'm glad he did. And he sells those boards, so you can get a kit, a set of them, but you still have to round up all the individual parts, many of which I had here already anyway. And here's the power supply that was on. I refurbished my original 8008 a while back and used a power supply out of an old computer, which gives me minus 12 volts, what requires minus 9 volts, so I used a voltage regulator, 12 to 9 volt chip there to bring it down to the 9 volts to run the memory board. The memory requires minus 9 volts as well as plus 5 volts. And it's running pretty good. There's only enough power there for 3 of the memory boards. And even at that, this heatsink on the regulator gets pretty warm. So we'll have to do something about that. But right now we're in the debugging stage and program writing stage. So we've got it running pretty well with the Arduino. And right now it's running the binary counter routine that's part of the original documentation. It counts from 0 to 255 and displays it on output 0, out 0, which is the bottom row of lights, 8 bits. And we also have a program here that we wrote that's a memory test program, a little memory test program. And we've been using that to check the memory cards out as we put them on. We found one bad 1101 chip so far with that little program, but so far so good. So we'll do a little run through here with some of the commands, and I'll put the camera on a tripod for that. Should make it a little more stable. Won't be bouncing up and around, getting everybody seasick. Okay. Let's see if we can get a good shot of the screen as well as lights. Output lights on the computer. First thing we'll do is we'll load the monitor program inside the Arduino compiler, IDE, serial monitor. There we are. Says you have the SD card loaded, which is nice. We need that. Mark 8's going. Power is off. Mode is jam. Execute step. And the register, the switch register, right now is at 0 when we started. And we want to, first we want to do is set the machine up the way we want it to be, just like we were pushing the buttons. Except instead of pushing the buttons, we have keyboard commands now to do that. So let's do a stat, see where we currently stand. Okay, it says, because I was playing with it before, we're running, and we have power off, mode interrupt. And hard to work the keyboard from this angle, but we'll get it. And we'll do the stat again just to make sure. Stat gives us the status of the switches going into the computer. And as you can notice, the lights stop blinking. We're at on interrupt mode. The power's still off. I haven't connected the power switch yet. Power switch is right over here now, and we turn that on and off manually. For interrupt mode, we want to be in jam mode, so we'll set it to jam. Do a stat again, see where we're at. Alright, we're at jam mode, step mode. Now what we're going to do is we're going to load a command file to, well, let's start by loading the memory test, this memory test program. Now I have the hex output from the assembler. I have the hex format, Intel hex format, stored on the SD card, so I'm going to load that with the LH command for load hex, and tell it that I want to read memtest, MENTEST dot HEX. Alright, it loaded the hex file, and you can see one of the lines there. Loaded it in, and it's ready to run. So first thing we'll do is we'll put it in int mode, interrupt mode. Set the switch registers to 5. All my entries are in octal unless I specify otherwise. 5. So you can see our switch register contents now are 5. It puts them out in decimal, hexadecimal, octal, and also binary. So it's useful for debugging. You can see whatever base or radix you're working in there. You can go right to town. Okay, so we're in int mode. Do a stat again. Let's see where we're at. We're in int mode, but we're in step mode yet. So let's do a run to start the computer. Okay, it's ready to run, and there she goes. She's just taken off to beat the band. Went through the memory test program, and she stopped at location. Here's the location where she stopped at 32, which in the program, if you look at it, when the memory tests out valid, it goes to stop. All the memory's tested, it's all fine at location 32. So that's where we want it to be, and that means it was a successful run. 377 halt. Now if we'd had an error, it would have gone out to 65, location 65 in octal. Would have stopped at 52, which means we had an error. And the first thing the error will do is it'll store the H and L registers out here, so we know what location we had the error in. Now we'll load a command file. That was an example of loading a hex file. We'll load a command file to restart the counter. And this is called bin counter, binctr.cmd for command file. So we'll read that, and it executes that one automatically the way I have it set up. So you'll see that we're now back to our bin counter. We reset the computer at the beginning of this sequence. Back up on the monitor so we can see that. Let's make it a little bigger. So we read the bin counter command file to control the console. So the first thing in that file was a step command, then a jam command. SR0 to 0 the register. We checked it out, and H and L are set to 0. Then we deposited a 26. Deposited a 0, deposited a 6. These are all actually instructions. When we first started, we hand assembled this program, so we stored everything in octal there. And when we get it all into the memory, the D is like pushing the deposit on the, we're actually pushing buttons here. It's what we're doing, switches. We get to set switch register 5 for our interrupt command. Put ourselves in interrupt mode and run mode. Hit the interrupt button, and boom, she's off and running. Saves a lot of time for the entry and to play around with it. And we use this ASM 75 opcodes, or two sets of opcodes for the 8008 from Intel. They had one version come out in 72 with the release of the original chip. And 75 they changed it, made them a little bit easier to use, a little fancier. We're using the 75 opcodes, which we hadn't used in the past because we didn't know about them when we built the original machine. So we stuck with the original opcodes, but since we're updating everything, we went with the new opcode set here. And the V75 is that's what I call the assembler, ASM V75 for this version 75. That's a brief rundown, and it looks pretty good. It looks like we're coming along really well here. We still have some work to do to get our final case put together, clean up that wiring back there some, and then we'll start putting additional features on the machine. We'll update that power supply, and we'll be off and running. Thanks for watching.